In Unit 10, we're going to expand on what we did in Unit 9. We learned the basics of integration in Unit 9, integration being the area under the curve, and now we're going to expand on some more strategies for doing integration and also a couple more uses for integration. So let's start with 5.5, indefinite integral and u-substitution. So before we get started on what's written down here, I want to really talk about how we can work on this. So if you notice, x squared plus 5 to the third, that looks like something that's a chain rule. Well, I don't have a strategy for solving a chain rule yet. And today we're going to use that. We're going to go over something that will help that. So if I could simplify it and make it the integral of u cubed du, well, this I know how to take the integral of. I know how to take the antiderivative of u cubed. That's 1/4 u to the fourth plus c. So what we're going to do is actually it's called u-substitution, and we're going to let u be x squared plus 5. So then my du, I'm just going to differentiate, and I get 2x dx. And notice that's a piece that's right here. So now I can really easily and nicely, instead of writing it as the integral of x squared plus 5 cubed times 2x dx, I can now write it as the integral of u cubed du. So this whole piece of 2x dx becomes my du, and then the x squared plus 5 becomes my u. So now it's u cubed du, and then I take the antiderivative, which no problem there, and then finally I plug back in. Is x squared plus 5. Now this might seem pretty complicated, but I think the more you're going to do this, the more you're going to get the hang of it and see that it's not that difficult. So just to prove that we've done it correctly, let's take this and take the derivative of it. So hopefully you notice this is a chain rule, so the 4 will come down, and we have x squared plus 5 to the third power, and then I multiply by what? By the baby, the derivative of the baby, which is 2x. So the 4 and the 4 will cancel, and I just get x squared plus 5 cubed times 2x. And notice, yes, that is exactly what we were given at the beginning. So, yep. Doing it this way definitely got us the antiderivative of what we were looking for. Remember, until you're confident, I want you to always check with taking the derivative. All right, so here's the general rule for this. It's the integral of f prime of g times g of x dx. That's going to be the integral of f of u du, which will give us f of g of x plus c. So this is exactly what we did, and it's the same as the chain rule. So if we went this way instead, I would take the derivative of the mom, leave the baby alone, times the derivative of the baby. And notice that's the same thing that we get over here. So to go backwards, I need to do this little intermediary step of u-substitution to help me undo what I needed to do. Right, let's practice a couple. So first thing I'm going to do is set u equal to 3x plus 2. I'm always looking for the baby. It's always the thing on the inside or the more complicated piece. So then my du is 3x dx. Now, take a look at what we have here. Here's my u. That's nice. And here's my dx. That's nice. But I have this 3. That's not helpful. It's just a 3. That's not super helpful. I don't have a 3. So I need to move the 3 to the other side. Since I don't have a 3, I'll divide both sides by 3, and I get 1/3 du equals dx. So now when I rewrite it, my 1/3 has to come along. So now the du and the 1/3 are together. So here's 1/3 du, and I have 1/3 and du. So now I take the antiderivative. So what gives me the derivative of sine? It's a negative cosine. And the 1/3 just comes to the right of u. plus c. And then we'll plug our u back in. Negative 1/3 cosine of 3x plus 2 plus c. So just like when we learned chain rule, this is not easy to get the first, second, or third time that you do it, but the more you do it, the more it will become very natural, and it will be just as easy as chain rule is now. But it does take a lot of practice. All right, for here, same thing. We're going to find that difficult piece on the inside and call it x squared plus 1, and then I differentiate it, and I get 2x dx, and I have an x and a dx, and that's good, but I don't have that 2, so I need to move the 2 to the other side. So that's 1/2 du is x dx. So now I can rewrite my integral as 1/2 the integral of the square root of u du. And we'll rewrite that with an exponent. That's u to the 1/2 du. And now I add 1 to my exponent, so 1/2 plus 1 is 3/2. So that's u to the 3/2. The 1/2 is still here, and then I multiply by the reciprocal of 2/3 plus c. So we can reduce that and make that just a 1/3. And then u to the 3/2. Oops. So my u is x squared plus 1 to the 3/2. And then plus c. Now for this one, we need to see what's the most complicated piece. And I'm also thinking, if I take the derivative of what, do I get the other? So my u is actually going to be this up here, the square root of x. And let's talk about why. So if my u is square root of x, that's x to the 1/2, then my du is 1/2 x to the negative 1/2 dx, or 1/2 square roots of 2, 2 square roots of x dx. Now take a look at what I have. I almost have that. I have 1 over the square root of 2. So that's really nice. 1 over the square root of x. So that's really nice. Oops, I forgot to write my dx. So now I just need to take care of this 1/2. So I'll multiply both sides by 2. So 2 du is 1 over the square root of x dx. So now I have 2 times the integral of e to the u du. The antiderivative of e to the u is still e to the u, so 2e to the u plus c. So 2e to the square root of x plus c. And again, I really encourage you to take the derivative of these and to make sure that you're getting them correct. You're going to want to keep taking the derivative every time you take an antiderivative until you feel super confident about them. And maybe even after that, because if you have a way to check it, why not check your work and see that you're right? All right, let's take a look at example 5 on page 432. Again, same thing. This will be our u, our complicated looking denominator of 4x cubed minus 1. So then our du is 12x squared dx. Now we have a couple things going on here. This 5 is not included anywhere. So let's move it onto the outside. So I'm going to first rewrite this. And now I see that I have x squared dx, which is exactly what I have here, but I need to take care of the 12. So let's move the 12 over. So it's 1/12 du is x squared dx. So now we'll multiply this by 1/12, so it'll become 5/12 on the outside of the integral, and then 1 over u du. Now 1 over u should look really familiar because it's an antiderivative that you know. So the antiderivative of 1 over u is ln u. And remember, when we take the antiderivative of ln, I'm only allowed to put positive things into natural log, so it's always going to be the absolute value of ln, I don't know why I wrote y, of ln u plus c. And now we'll substitute back in. So it's 5/12 natural log, the absolute value of 4x cubed minus 1 plus c. Again, I really encourage you to try that again on your own and make sure that when you take the derivative, you get back the original function. All right, and then here, again, my more complicated piece is going to be my u. So it's e to the x plus 4. My du is just e to the x dx. And here I don't have anything that I need to substitute on the outside or solve for because I have e to the x dx. That's exactly what I want. So now it's just the integral of 1 over u du. And again, that's a natural log. So the antiderivative is the natural log of absolute value of u plus c. And that's the natural log of e to the x plus 4 in absolute value plus c. So I'll reiterate one more time. It's really important that you practice these again on your own, and not only that you practice on your own, but you take the derivative to make sure that you understood exactly how we got the antiderivative. Now these two are a lot more complicated. I don't want to spend a ton of time on them because they're kind of ones that you want to commit to memory, but we will talk about them for just a second. So for the antiderivative of tangent, we're going to rewrite tangent as sine x over cosine x. And then we're going to let the u be the cosine. Because it's in the denominator, it's a little bit more tricky. And then my du is negative sine x dx. So again, I need to move that negative over. So now I can rewrite my integral as the negative integral from 1 over u du. And then that's negative natural log cosine of x plus c. Now there's some fancy work here. If we let this negative sign come up and be part of my exponent, because that's one of the properties of logs, I would have natural log and then cosine x to the negative 1. And this is not arc cosine this time. This is 1 over cosine is what this is telling me. And 1 over cosine is also secant. So again, this is probably not one that you want to reproduce each time, but you might want to memorize it. And same with this next one about secant. This next one's quite a bit more complicated, but we'll take a stab at it. So to do the integral of secant of x, so the first thing we're going to do is multiply by secant x tan x over secant x tan x, which I know seems kind of weird to do that, but the reason we're going to be able to do that is because then we're going to have something to use our u-substitution for. So let's multiply this out and we get the integral of secant squared x plus secant x tan x over secant x plus tan x. And now we're going to let u be secant x plus tan x. So then my du is the derivative of secant is secant x times tan x, and then plus the derivative of tan is secant squared. So hopefully you now see that the derivative of the denominator is actually the entire numerator. I forgot dx. So now I can rewrite this as the integral of 1 over u du. And now this is pretty familiar, that this is just the natural log for the antiderivative of 1 over u. So the natural log of u plus c, and then we'll plug in what u is. That's secant x plus tan x plus c. So this is pretty complicated, and it's not like ones that you use all the time, but they are useful to have in your back pocket. So this is on page 436, so if you want to memorize them, it's not a bad idea at all. So a general rule for u-substitution is if I have the integral of the derivative in the numerator over the original function in the denominator, And then it will be the natural log of the original function plus c. Because what we're going to get when we take the antiderivative, or when we rewrite it using u substitution, is 1 over u du, which is the natural log of u. And again, u was our denominator, which was our original function, so it's the natural log of g. This is not something you need to memorize. This is something that you naturally see the more of these you do. Alright, so this problem so for this one I forgot definitely more complicated. We're going to still choose the more difficult part to be our u. That's 4 plus x. But when I go to take the derivative of it, I just get 1 dx. Well, I have a dx here, but I didn't take care of this x. So I'm going to need to do something else. And the something else is I'm going to solve for u. So the way I'm going to solve for u is I'm going to subtract 4 from both sides. So if u equals x plus 4, then u minus 4 is x. So now we'll rewrite this whole thing as the integral of u minus 4 times the square root of u. And let's rewrite square root of u as an exponent. So that's the integral of u minus 4 times u to the 1/2, and then we can distribute that to both pieces. So that's the integral, that's u to the 3/2 minus 4 times u to the 1/2. And now that I have this done a little bit more clearly, I can take the antiderivative, now that it's all in one variable. So the antiderivative of u to the 3/2, I'm going to add 1 to the exponent, I get 5/2, and then I multiply by the reciprocal. Minus 4, u to the 1/2, I add 1 to the exponent, I get 3/2, and I multiply by the reciprocal of 2/3. And then I'll substitute in what u is. U is 4 plus x. I really encourage you to try this problem a second time and maybe even a third time, because it's a pretty difficult concept, but it's really important and used pretty often. Now on page 437, example 8, they talk about some other functions that are a little bit more complicated, a little bit different. Hopefully you notice that this is really similar to arc sine, which is 1 over the square root of 1 minus x squared. So before I can use that, I need to rewrite what we're given into that form. So the first thing we're going to do is factor the 4 out. So I get the square root of 4 that we're going to pull out, and that's going to leave me with 1, the square root of 1, minus x over 4, x squared over 4, and then dx. So that's going to become a 1/2 on the outside, the integral, because the square root of 4 is 2, and I'm going to pull that out in front. And then I want to write that so the whole thing is underneath the squared, so that's x over 2 squared, because 2 squared is 4. And now we can use our u substitution. My u is x over 2, and then my du is 1/2 dx. So then if I just want to get the dx by itself, I have 2 du is dx. So now I have 2 over 2 times the integral of 1 over the square root of 1 minus u squared du. And now I have arc sine. So that's going to be arc sine of u plus c, which I can write as sine to the negative 1. And instead of u, it's x over 2 plus c. Again, this is another one that's pretty complicated and goes really quickly, so you really want to try this again. Again, the book does it out for you on page 437, so please feel free to follow along with that. Now for this one, hopefully you see that this one also does look familiar. Hopefully you see that this looks like arctan, which is 1 over 1 plus x squared dx. So we need to first factor out the 9. So let's pull a 1/9 out of everything. And we're left with 1 over 1 plus 4 over 9 times x squared dx. And same thing, I need to get that whole thing underneath that square. So 1 over 9 times the integral of 1 over 1 plus, that's 2/3 x and the whole thing squared dx. Now I can do my u substitution of 2/3 x, and then my du is just 2/3 dx. So again, I got to make that 2/3 come to the other side. So 3/2 du is dx. So 1/9 times 3/2, the integral of 1 over 1 plus u squared dx. So now we can take the antiderivative. We have a 1/6 out in front, and the antiderivative of 1 over 1 plus u squared is arctan. So tan to the negative 1 of u plus c, or 1/6 arctan, and my u is 2/3 x plus c. All right, so I forgot my squared, and this is actually supposed to be 4 minus x squared. So my u is 4 minus x squared, and then my du is negative 2x dx. So I have to take care of that negative 2, so that becomes a negative 1/2 du is x dx. So now I have negative 1/2, the integral, the square root of u du. So this is important here that can't write these integrands to be 0 and 2 anymore, because those are when I'm talking about x values. Now I have to talk about u values. So if I want to write integrals, there's two different ways to do this. I can find them for u. So when x equals 0, u is, I'm plugging it in right here, 4 minus 0 squared, or 4. And when x equals 2, u is 4 minus 2 squared, or 0. So now I go from 4 to 0. So again, this is way 1, and then I'm going to show you a second way in a minute. And we're going to go from 4 to 0 of u to the 1/2 du. So we'll add 1 to the exponent, and we get u to the 3/2. We multiply by 2/3, and we still have the negative 1/2 out in front. And now with our new endpoints, we're going to evaluate this function from 4 to 0. So we can simplify before we do that. Let's see, our 2's will cancel, and this will just become negative 1/3 u to the 3/2 between 0 and 4. All right, so let's plug that in. Negative 1/3, 0 to the 3/2 minus 4 to the 3/2. And if you're not sure how to simplify 3/2, let's talk about writing it as with the radical. So that's negative 1/3, 0, and then that's the square root of 4 cubed. So the denominator comes out and becomes the radical, and the numerator stays as the exponent. So that's 2 cubed, or 8. So that will be a negative 8 minus a negative 1/3, which is a positive 8/3. Now, as I said at the beginning, there's two ways to do this problem. We can rewrite our endpoints now that they're 4 and 0, or we can substitute back in at this point for our original x values. Either way, we're going to get the same answer, but I'd like to show you that on the next slide. Let's go to this point. We have negative 1/3 u to the 3/2, and I'm not going to talk about my endpoints just yet. So let's substitute back in my u, negative 1/3, and my u was 4 minus x squared. That whole thing is to the 3/2, and we're going to evaluate it with our original endpoints of 0 and 2. All right, so 4 minus 2 squared is 0. To the 3/2 is still 0. And then 0 squared 0, so 4 minus 0 is 4 to the 3/2. We can rewrite that as the square root of 4 cubed. So that's 2 cubed is 8. So we get negative 1/3 times a negative 8, or a positive 8/3. So since we get definitely the exact same answer. It's a personal preference of which one you like to do. If you like to change the endpoints, then you're welcome to do that. It's a little bit more work up front, but you don't have to worry about plugging the U back in because you've already changed the endpoints. If you prefer not to change the endpoints and just plug the U back in, you're welcome to do that as well. It's really a personal preference without any actual difference in how you're graded or scaled on the AP test. So this one looks like a really complicated problem, but we're going to use a lot of different small rules to try and help us make this as simple as possible. So first we have this divided by 2, which is a 1/2. So let's pull the 1/2 out. And now already we don't have a fraction, and that looks nicer. The next rule we're going to do is we're going to distribute this integral to both pieces. So I can rewrite it as negative as 1/2, and then the integral of 1, 0 to pi, and then minus from 0 to pi, the integral of cosine 2 theta, d theta. And as you can see, I forgot to write my d theta, but that's important because it tells me what the variable is. In this case, my variable is theta. So now let's integrate these pieces. The antiderivative of 1 with respect to theta is just theta, and we're going to evaluate that from 0 to pi. And my 1/2 is just hanging out on the outside waiting for me. But let's take a look at this one. Hopefully you see that there's a u in there. I need to take care of that 2 theta. I don't know what the antiderivative of 2 theta is. I just know the antiderivative of theta. So let's go ahead and rewrite that. So we have our u is going to be 2 theta. So then our du is 2 d theta. And we don't have a 2, so we need to move the 1/2 on the outside. So 1/2 du equals d theta. So now this integral from 0 to pi of cosine 2 theta d theta actually becomes 1/2 the integral of cosine u du. And now the antiderivative of cosine is sine, so that's 1/2 sine u, and we're going to evaluate that. Now, I don't write my endpoints because I didn't change them. You could change them. It's up to you if you want to change them. If you don't change them, then you have to go back to 2 theta on the inside. So 1/2 sine of 2 theta. And I'm going to evaluate that between 0 and pi. So let's write that here. Okay, so now let's go ahead and start simplifying this. We have the 1/2, and then it's going to be pi minus 0 when I plug in pi into theta, and then minus 1/2 sine of 2 pi minus minus 1/2 sine of 2 times 0, or 0. Okay, so let's take each piece. That's going to be 1/2 pi, and then we have minus sine of 2 pi. So let's take a look at what sine does. It goes 0, 1, 0, negative 1, 0. So 2 pi is right there at 0. And sine of 0 is also 0. So minus 0. So we just get 1/2 pi, or pi over 2. So you would get, again, the same answer. If you worked on changing the endpoints up here, you could do that. It's really personal preference, whichever you want. So we could have said when theta equals 0 and when theta equals pi, what does u equal? Well, we'd plug it into our u. So 2 times 0, u would be 0, and 2 times pi, u would be 2 pi. So you would get the same answer, but you would have a little bit less work, but it's really your choice of what makes sense to you. So now we're going to talk a little bit about even and odd functions. This isn't a super important concept, but it can be a little bit of a shortcut if you are good at them. So in even functions like x squared, where my exponent is even, what happens is that my function is symmetric around the y-axis. and it either both points up or both points down on my endpoints. So in this case, as it would be in x squared, my end behavior is going in the same direction. It could be like negative x squared, and it would be going to the negative infinity in my end behavior. But the important part about an even function is the end behavior is exactly the same. So now if I go from negative a to positive a, so if these numbers are the same and my function is even, again, symmetric about the y-axis, then the side on the left is exactly the same as the side on the right. So I can go just from 0 to a and multiply by 2. So you can see how that would save you a little bit of time at the end when you're plugging in. If my function is odd, like x cubed is an odd function, again, we're symmetric about the y-axis, but one ends in the positive direction and one ends in the negative direction. And what happens here is that if we go from negative a to positive a, there's the exact same amount of area under the curve in the negative part as there is in the positive part, so this just becomes a 0. And again, you can definitely see how that could be a shortcut if you recognize it.